Welcome to the lecture series of VLSI technology with the subject code KEC 053. So in the last few lecture, we were discussing about the epitaxial growth, that how the epitaxy layer is grown, what is the use of epitaxial layer, and how many methods are there to grow the epitaxial layer. So briefly, we have studied about the liquid phase epitaxy, vapor phase epitaxy, and molecular beam epitaxy. All three epitaxial process we have covered, right? Because we know that silicon, its melting point is very high, so we cannot use liquid phase epitaxy to grow the epitaxial layer over the silicon. So to grow the epitaxial layer over the silicon, we always need to have vapor phase epitaxy and molecular beam epitaxy. And the difference between the basic two epitaxial process, molecular beam epitaxy and the vapor phase epitaxy, is vapor phase epitaxy is carried out at very high temperature, whereas molecular beam epitaxy is generally carried out at low temperature, and we can have a very thin layer of epitaxial layer with the help of molecular beam epitaxy, right? So because in case of VLSI technology, we are reducing the size of each transistor, we are reducing by dimension. So we also have to reduce the dimension of epitaxial layer. So this epitaxial layer, when we go down in the technology, we can reduce the epitaxial layer dimension by molecular beam epitaxy. And second thing is, when we go down to the dimension length, when we decrease the transistor size, when we go from 180 nanometer to 45 nanometer or 28 nanometer or beyond that, the short channel effects will come in picture. So it is not possible to have the good performance of the transistor with the help of simple CMOS fabrication steps. So the topic of discussion, that is your silicon on insulator, today will tell you how we can fabricate the devices over a silicon wafer, so with the enhanced performance. So what basically is a silicon on insulator? So silicon on insulator, it uses the 3-layered substrate. We can see here we have a 3-layered substrate and 3-layered substrate in place of conventional bulk silicon. So instead of your simple substrate, we have the simple p-type or n-type substrate in case of CMOS technology, right? So instead of that, we are going to have now silicon substrate. Above that, we will have the buried oxide, and over that we have a silicon layer, and in this silicon layer we are going to fabricate the transistor. So this layer lies upon the substrate and isolates the body from the substrate. So the very first advantage we can see in the diagram, that this BOX layer will isolate the silicon channel from the substrate. So it provide a proper isolation between the two. So and the transistors are built upon your transistors will be built upon this thin silicon layer, which will be with the full dielectric isolation of the devices, which will reduce the parasitic capacitance. So hence the overall performance of the transistors can be improved. And the choice of this layer, buried layer, and above that this silicon layer, is dependent upon the application. So when we talk about the circuits which are working on a radio frequency waves, at radio frequency waves, we generally have the sapphire. So okay, so we generally used to have the sapphire when we work at a radio frequency waves, and your silicon dioxide is used for to overcome the shortcoming effect in microelectronics devices. So what is the need of this SOI? So according to Moore's law, when we go down the technology, the number of transistors will be increased by every 18 months. Right. So every 18 months, the number of transistors which are present on a single area, on a given area, it will be doubled in every 18 months. So when we go beyond this 28 nanometer technology, with an upgrade to traditional planar bulk CMOS technology, there are n number of effects that comes in picture, and these are known as short channel short channel effects. Okay, so these effects will they will increase the leakage current. Okay, they will increase the leakage. Parasitic will be increased. Okay, parasitic capacitance will be increased. So, so the overall device performance will be decreased when we go down the technology scale. So, increased complexity of scaling of complex conventional bulk CMOS technology cannot handle these effects. So, to avoid the interaction between the devices and the substrate, which gives rise to some unwanted parasitic capacitance, mainly due to the parasitic capacitance developed between the source and the drain, we need to have this SOI technology. The next drawback is sometimes when we go down the technology, when we reduce the VDD and the VSS supply voltages, there will be a short channel effect in there will be a low resistance path between VDD and ground. This is the fabrication diagram of simple CMOS inverter. So, if I explain with the help of circuit, we have this CMOS circuit with VDD and VSS, and this is your output terminal and input terminal. So, sometimes there will be a low resistance path between VDD and ground. This is known as latch up. This is known as latch up because we know that in case of CMOS technology, at a time one transistor will work, either this will work or this transistor will work at a time. So, but because of this latch up effect, there will be a low resistance path from VDD to ground, and there will be a leakage current, and hence your device performance will be decreased. So, let us see how this drawback can be removed with the help of this SOI technology. So, in SOI technology, we have the silicon substrate. Your buried oxide is deposited over this silicon substrate, and then we have this silicon area where your PMOS, where we have this PMOS and NMOS, where we fabricate the PMOS and NMOS over this silicon area. This complete is the silicon area, right? So, because of this buried oxide, we know that this act as a proper insulator. So, there will be no, we can see that there will be no short circuit path between VDD and ground. So, this way we can reduce this latch up problem. Some parasitic capacitance will be reduced, leakage current will be less, and we will have the better performance. The full dielectric isolation of the device reduces the parasitic capacitance. So, we have seen in the previous diagram. So, it will reduce the parasitic capacitance, thereby it will increase the performance, improve the performance, and your short channel effects will be reduced. And as the transistor shrink, the length of the gate is also reduced. The control of the gate over the channel region is also reduced, and thus which will lower the transistor performance. So, SOI provides more control over the channel using the body biasing. So, we can bias the substrate also, so that we can have a more control over the channel. And to reduce the growing leakage part due to the sub-threshold leakage and diode leakage current, we can use this technology. Next is to reduce the manufacturing complexity while continuing to delivering the high performance at lower cost with the lower power consumption. So, these are some advantages of this SOI technology. So, let us see that how many types of SOI devices we can fabricate. First one is partially depleted silicon on insulator. It is known as PDSOI. In case of PDSOI, a silicon layer is thicker and the holes are pushed towards the buried oxide layer, which will create a floating area where your charges can be stored. that creates a modified switching threshold point. So, as per the charges present in this floating area, they will modify the threshold point, and which depends on the history of the charge. Sometimes it may happen that when we switch on the device, some charges are already present in this. So, this, because of this floating area, the history, some history will be there, and this will change the threshold point of the device. The inversion region does not extend the full depth of the body, and will have some floating area in this PDSOI technology. The insulating buried oxide layer is also thicker, and the channel is lightly doped. The partially depleted SOI devices behave similarly to the bulk devices, except that we have some charges which are already present in the body. Okay, so this technology is simple as compared to your CMOS technology. We know that in case of CMOS technology, when we have to fabricate a CMOS, right, we suppose this is your p-type substrate, we have to create one N-well, right, N-well, where we will fabricate the PMOS, and in this we will fabricate the NMOS, right. So, no creation of wells and trenches will be there in case of PDSOI technology. So, with the help of this SOI technology, we will have this buried oxide, then silicon. Over this silicon, we will create our transistors. So, the insulated box layer, this buried oxide, the thickness of this buried oxide varies from 100 to 200 nanometer. The top silicon layer varies from 50 to 90 nanometer, and this is highly recommended for analog circuits, so that we can store some charges, we can use those charges for the future, and it has the doped channel. Next is problem associated with this PDSOI. The only problem associated with this PDSOI is the history effect. The body of the PMOS and NMOS transistor in PDSOI is floating instead of tied to VSS or VDD, right. So, due to the difference in the body voltage, your threshold voltage can be changed, and this could cause a little delay in the calculation. There will be a little delay in the calculation, so mismatch will be there between the two identical transistors. So, as the SOI circuit switches, the body voltage of the switching transistor will change from their previous state to next state, and this is called the history effect. So, because of the floating area, there will be some charge stored already. So, when we apply a new voltage, it will that effect will also comes in picture. So, this is called the history effect. The exact voltage depends on the history of the source, gate, and the drain voltage, which leading up to the current time, and the body voltage affects the conduction of the channel, and therefore the switching speed and the parasitic capacitance of the complete device is also affected. And lastly, we can see that in case of PDSOI, your MOSFETs, they need a very high channel doping to suppress the short channel effects. Next one is your fully depleted silicon on insulator, technology. In case of FDSOI, your planar process technology with two major changes are there. In case of partially depleted SOI, we have a very thick layer of buried oxide, but in case of this FDSOI, we have a very thin silicon layer placed over a very thin buried oxide layer. Your buried oxide layer is also very thin in terms of ultra dimensions. So, the silicon layer under the gate is so thin, and that is fully depleted of the mobile charge carriers, and there will be no doping. So, no doping is required inside the channel. So, when the channel is very lightly doped and very thin, your depletion region fills the full length of the body, and thus remove the floating body region. So, in this case, we have the advantage that no floating body will be there and no history charges will be there, and we have a very thin silicon buried oxide. So, the combination of these two, So the combination of these two variations are called ultra thin body and the buried oxide fully depleted SOI. And it is named as UTBB FD SOI technology. This is the diagram for fully depleted SOI technology. In case we can see here that we have a very thin ultra thin BOX layer. We have the silicon substrate, buried oxide, and we have the silicon layer over source and drain areas are defined. So the insulating buried oxide layer lowers the parasitic capacitance between the source and drain. The insulator layer efficiently removes the parasitic capacitance, hence it will increase the device performance. The operation will be faster at the lower voltage and better power management will be there. Your body is more effectively, your body terminal can be more effectively used to control the transistor, and the top silicon layer in this case varies from 5 to 20 nanometer. The box layer varies from 5 to 50 nanometer. It is this fully depleted technology can be used for low power applications and undoped channels. So this is the structure where we can apply some voltage at the substrate end and we can use this as a vertical gate. So body biasing is a process where we can apply where your device performance can be increased by applying the voltage at the substrate terminal. This method is known as body biasing or substrate biasing, and it is sometimes also called the back biasing effect. So the creation of channel between the drain and the source results in fast switching by applying some voltage at the substrate end. So we can have we can change the biasing potential. Here you can see that your VG in this diagram, VG is greater than V substrate, and in this diagram we can see that V substrate is greater than VG, right? So if you reduce the value of gate voltage, we know that your power dissipation is directly proportional to VDD. So if you reduce the value of this VDD gate voltage, if you reduce and it is also proportional to this VG, if you reduce this value, we can have the lower power dissipation. So for lower power dissipation, we can use this mode where we can apply less gate voltage and more substrate voltage. And for high performance mode, we can use the supply voltage in this way. So we can vary the supply voltage at gate terminal and at substrate terminal, so that we can have a n number of performance n number of characteristics for a single device. So this is the fabrication of SOI technology, that how this fabrication is done. So we have this silicon substrate, over this buried oxide is installed with the help of epitaxial process. Then we have this silicon film. Your transistors will be fabricated in this silicon film. Okay. So now with the help of photolithography, this area will be removed and we will have a defined area for two transistors, right? For this is for first transistor and this is for second transistor. It can be NMOS and PMOS, that we'll see in the next slides. So next is we form the gate over these areas. So your gate is fabricated with the help of photolithography. Then so polysilicon gate is fabricated. Now we will implant the P plus doping to create here PMOS. Okay, your P plus doping is done with the boron. So in this diagram we can see that this area is protected by mask. This area is protected by mask, so that your boron impurities cannot they do not disturb the qualities of this area. So this left hand side area is masked and we can have the boron doping over this area only. So after this doping is done, here we can see that your boron doping is done, your P plus doping is done. Now we have to dope by N plus impurities by arsenic, so that we can create the NMOS. So this area is shielded by some mask, and then arsenic gas is passed over this area, so that we can have N plus regions. So that we can have N plus regions over there. So once these areas are defined, the final process is metallization. So by the metallization process, we define the areas where we need to connect the metal lines. So advantages of this SOI technology over bulk CMOS process is we have a better electrostatic control over the channel, reduction of parasitic junction capacitance will be there, excellent latch up immunity. We have seen that with the help of buried oxide, your VDD and VSS are completely isolated from each other. Limited short channel effect as compared to your bulk CMOS technology, reduced subthreshold leakage current and diode leakage current will be there. They can be used for higher speed and low power consumption. It gives high performance, cost effectiveness as compared to your bulk CMOS technology. Smaller transistor saves a lot of area, which provide a high package density, because no area is saved by removing the well and trenches areas. Next is radiation tolerance. It reduces the soft error rate, which refers to the change of data in the memory for the space application because of the radiations. It involves fewer manufacturing steps as compared to your bulk CMOS technology, because no wells and trenches are there. Next is your substrate noise is reduced because of the buried oxide layer, which act as a dielectric material. The only problem, a few problems are there with this technology, that it has a self-heating effect due to the low thermal conductivity of the oxide. Second one is your history effect, and the third one is the difficulty in manufacturing this thin body SOI wafers in case of FD SOI. So overall, this technology is useful to, for the future purpose. So we are continuing. We are manufacturing the ICs with the help of this technology. So thank you very much.